All right, let's get started. As a reminder, your one-page report, which has to be in PDF, is due by next Wednesday, 11:59 p.m. There's a post-up with a bunch of details, and also look at the mini project page for more details on what's needed and stuff. Two important things: please form your group on Autolab first before submitting a report. If by chance you've already submitted a report, form your group and submit it again. And the important point to note is when you're picking your case studies in references, make sure you have URLs, because what I plan to do is on the page of chosen case studies, I'll have a URL that points to an article or whatever that's relevant for your case study. Any question on the mini project or the report? Alex.
Do you have some format you need the citations?
Alex question, do you need the citations? No, anything is fine. Evan.
What is a good reference?
Evan's question is, what is a good reference? I'm not quite sure what you mean.
So what are we allowed to source?
Here's the question, what allowed? You can source anything and whatever you want.
Okay.
There are no restrictions. Any other questions? I mean, ideally what you refer should be relevant to what you're saying, but I don't know. All right, homework 4 is now posted. We are trying something new with homework 4. There are some bonus points on question 1. So the 3 fastest submission in Java and the 3 fastest submission in Python and the 2 fastest submission in C++ will get 4 bonus points. However, there's a big warning. These things can take up a lot of time. It's probably not worth your effort if you're not done 2 and 3 already. So I would recommend, aim for the bonus points if you are done with your homework and you have spare times on your hand. Okay. Any questions on this, Stephen? 3 fastest in Java, Python, and 2 fastest in C++. Because there are much fewer submissions in C++ than other languages. Sorry?
Was that the case for the last?
It has been the case for all the programming assignments that have been submitted so far in all of history of CSE 331. And so the question is, what if you switch your language? Your last submission is what is always counts. So yeah, there's no loophole where you can submit all 3 and get 12 bonus points, for example. Any other questions? All right, so what we're going to do today is do a runtime analysis of the breadth first search algorithm. And in the process, we'll kind of hand wave a bit, but once you have analyzed BFS, the analysis of DFS is fairly straightforward. So as a quick reminder, 2 data structures we're going to use are stacks and queues. Stacks is last in, first out. Queues is first in, first out. We looked at a couple of representations of graphs, adjacency matrix and adjacency list. And the adjacency list is better for traversals because of many reasons, but among other things, the thing that we're crucially going to use is that if you want the list of all neighbors of a given vertex U, you can do it in time that's linear in the degree. So the number of neighbors of U, not the number of vertices. And it turns out that space-wise, it's also more efficient. Okay? And so definitely for traversal, adjacency list is better. But I think I mentioned this last time, pretty much for any algorithm that we're going to cover in this course, we are by default going to go with adjacency listing representation. Okay? So as a general thing, if in the homework the problem talks about a graph, unless it specifically says adjacency matrix, you should assume it's represented in the adjacency list format. Questions? All right. So I did this proof You spent a bunch of time last time, so I'm not going to go all over it again. And if you were here before class, the proof video also went over the proof. But basically, what's known as 2 times m is exactly the same as the degree of all the vertices. And this is a fact that is really useful when you're doing runtime analysis and such. So here's the version of the breadth-first search algorithm that we have seen. It's essentially constructing layers. You start off with layer 0, which has a start vertex S, and at any point of time, if you have constructed layer 0 to layers j, in j+1, you look at vertices that have not already been covered, but are connected by an edge to the previous layer. And you keep on doing this till the new layer that you're trying to create turns out to be empty. So, and we'll walk through this, but as a quick, so we're going to actually analyze the runtime of this algorithm. For this, we have to specify our data structures. So as I said before, the graph is going to be the adjacency list format. For the layers, we're just going to use linked lists. So you're going to have one linked list for each layer. And we need a quick way to figure out whether a certain vertex V that we are considering has been already is in one of the layers or not. And for that, we're just going to maintain a simple array that keeps track of that. So it's called CC of V, that also CC, again, as before, denotes the connected component. So remember, if we have already, if we are trying to add a vertex into a layer in run of a BFS, that means that that vertex is indeed connected to your start vertex. So these are the data structures that we're going to use. Any questions? So again, graph adjacency list, layers via linked lists, and to figure out whether a vertex is already present on the list or not, we'll just have a Boolean array that keeps track of that. So the plan next is to go ahead and do the runtime analysis for this. But before I go on, any questions on this BFS algorithm, anything about graphs, the property that 2m is sum of the degrees? All right, so we're going to do a quick runtime analysis of BFS, and then we're going to walk through. So here we're having different layers as being distinct linked lists. We're going to make a simple observation that you can combine all of this list together into one queue, and then the analysis of that actually turns out to be even simpler. And then we'll quickly see why that analysis implies a similar runtime analysis for the DFS algorithm. All right, so if you want to do a runtime analysis, we should have the algorithm written out. So let me do that again. So you're trying to run BFS with the start vertex of S. You initialize this connected component Boolean variable. You say you already have encountered S, so you set that to be true. And the connected component of W is false for all of the vertices. So S is connected to itself, and you don't know anything about the other thing else. Then you just initialize index, and your initial layer is S. When I say L0 is set of S, I mean this is when you create a linked list with S in it. Okay. So this is a linked list. And so your algorithm keeps on running till the current layer that you're considering is non-empty. The very first thing you do is try to start the new layer for this. And again, this, remind you, is again a linked list. And in fact, it's a new linked list. So for each layer, you create one new linked list. And then what you do is you look at, so again, you have till layer I, and you're trying to create I plus 1. So what you do is just walk through all the vertices in the ith layer. For each search vertex, you look at, so here's my vertex in layer I. I want to look at all possible neighbors of U, right? So you look at all possible edges UW, and so W is now a candidate to be put into Li plus 1, but you need to first check whether you have already visited it or not. So the only time you're going to do something with it is if you have not already visited it. If that's the case, then you first say you have visited it, and then you add and once you have gone through all the vertices in Li and all of its neighbors, you increment your index. And so that's it. So this is the thing. If you wanted to also construct the BFS tree, you could have done it, and that's what the book does, but we're not going to do it explicitly because it's not immediately relevant to the runtime analysis. Okay. Again, any questions on this statement? Is everyone clear what data structures we are using? Okay. So I guess technically I should also say G is part of the input and G is in adjacency list format. All right. How much time would step 0 take? More than O of 1. O of n. So I'm initializing n elements in the array. This is O of n. How much would 1 and 2 take? O of 1. So you have O of n here, O of 1, O of 1. So altogether, the first 3 steps will take you linear time. Okay. All right, so let's look at each step in my loops. Let's look at those steps first, and then we'll come back to how many loops there are and stuff. How much time would each of this step take? We're initializing an empty linked list. O of 1, right? How much time would all of these steps together take? O of n is correct, but you can do better. Oh, sorry. Yeah, outside, inside the 2 nested loops, sorry. O of what, right? You're just doing some simple checks and assignments. Okay. And again, this step is O of 1. Okay. All right, so we have looked at each individual step outside of the loops are all constant times. So essentially what you have to figure out is how many times do you kind of execute these constant time steps. Okay. So to do that, let me put in some notation. So let me call T12, and I'm using, oops, yeah. So you count how many times the algorithm reaches this for loop, right? So note that I already have 2 loops here. There's a while loop outside, and then there's another for loop. So that when I say T12, I mean how many times do you run the 2 loops together? So number of times algo gets here, and if you look at the innermost part, so this is where is the 3 nested loop, the outer while loop, and the 2 for loops, and I'll call T123 to be the number of times algo gets here. So just to make sure this makes sense, let me write down the total complexity of this algorithm, and then I'll take questions. So the total runtime is the first 3 steps O of n. I need another thing. So let T1 be the number of times the while loop runs. Okay, so number of times this loop runs. So you take O of n steps over here. The number of times that you're going to run step 3.1 overall, how much would that be in terms of T1? I forgot your name, sorry. Jared. O of T1, right? So to be more precise, you're going to get here T1 many times, and each time you get here, you spend O of 1 time getting here, right? So that's T1 plus O of 1, all right? Oh, I'm sorry. Okay, this should work. How many times would this block of instructions run for? I want you to tell me in terms of one of these t quantities. So as Stephen Mount, it's you run all of these guys T1, 2, 3 times. It's order 1. Plus if you look at this guy, it runs T of 1, 2 times. So T of 1, 2 times O of 1. Okay, so let's bound this further. So the first thing is still O of n. Now, the number of times that you run this loop is always smaller than the number of times you get to this position, right? Because it's much lower, it's much further down in the nested structure, right? So you can always say T1 is less than or equal to T123. By a similar reason, T12 is less than T123. So this whole thing is less than or equal to T123 plus times order 1 plus T123 times order 1 plus T123 times order 1. So this overall becomes O of n plus O of T123, which you can't see. Okay. And so now our job is we need to basically figure out how many times do you get to that if statement, like if connected component of W is false. Okay. Another way to think about all steps that we have done so far is that the runtime of the algorithm is dominated by how many times you run this chunk of 3 lines of code, which is nested in between all of your loops. Okay. Any questions on this? Is everyone comfortable with T1, T12, T123? Harshita.
How do you replace T1 and T1, T1?
Right. So the question is why are these two things true? So let's just look at T1, which hopefully is the simplest one. So T1 is how many times you run this loop, right? So T1 is how many times you get to 3.1 overall. Right? And the point is, if you get to 3.1, you're going to get to this line at least once, maybe more. So what that means is the number of times the algorithm runs this line is going to be more than the number of times that it runs this line, which by definition means T123 is bigger than T1. By a similar argument, if you look at T12 and T123, you know, for each time you get to this thing, you might run multiple of these guys, but at least one more. So that's why you have T123 is bigger than T1. Any other questions? Okay, so what we have to do in the analysis then is to basically bound T123, and the way we're going to do it is we're going to do it in steps. Ultimately, we want to argue that it's O of M. That's our final goal. And there is a way to directly argue it, which I'm not going to go through. I'm just going to walk through various steps. So first, we're going to argue that T123 is at most n cubed. Then we are going to argue its at most n squared. And then finally, we're going to argue its order n. So we're just going to progressively make it better and better. And so let's do the first analysis. Well, let's try to do the simplest bound. So we want to figure out how many times I get here. The simplest way to do that is to just argue individually how many times these 3 loops can run in the worst case and multiply them together. Right? So just to set everything, how big can T1 be in terms of n? How many layers, what is the maximum number of layers you can have when you're running BFS? All right, maybe a good time to talk to your friends. Let me know any questions. If not, tell me the answer for how many layers can you have in terms of n, in the worst case. All right, any questions? If not, any answers? Jared? N, right? So the worst case is basically when your graph is a line, right? So everything just connects 1 to 2, 2 to 3, 3 to 4, and all the way up to n, just a single line. Then each one of them will form their own layer, right? So in the absolute worst case, you will have n layers, and you cannot have more than n because note that each vertex can only belong in at most 1 layer. You cannot have a vertex appear in 2 layers, right? So if you have more than like n plus 1 or more layers, by the pigeonhole principle, you'll have 1 layer that's empty, right? And that can never happen. So I'm going to write this as an observation, which you can prove at home and is useful, is each vertex in V is in at most 1 Li, and that implies that the number of times you run this while loop, which is the number of layers you have. Oops. Okay. So, all right, so I'll move this back again, but remember T1 is the number of times you're running the while loop. Okay. So that's at most n. Now let's look at how many times this outer for loop can run. What is the absolute worst number of times this can run for? Jared? Yes, so actually n minus 1 is correct. Let's be safe and just say you're right, but we'll do an even dumber bound and let's say it's n. Because, well, how many times can this for loop run? It's the total number of vertices, right? Because every time you're running it, you're getting another vertex. All right, good. How many times can this loop run for? the simplest possible bounded. Again, just to be sure, when I say how many times this loop run for, I mean once the algorithm has come to this for loop, after that, how many times can it run? I have to ask your name, I forgot. Brendan? That's also n minus 1, but we'll again just say it's at most n. Because again, how many neighbors can a vertex have? It's at most n. Right? So what do we have? We have 3 nested loops. The outer loop runs for at most n times. The first inner loop runs for at most n times. And the innermost loop runs for at most n times. So if you have 3 nested loops, which in turn run for at most n times, how many times would it run in total? O of n cubed, actually just n cubed, right? All right, so this implies T of 1, 2, 3 is at most n cubed as each loop runs at most n times. And you can't see it. Okay. So that implies overall you have order n plus order n cubed, which is O of n cubed. Okay. Now, if we just wanted to show that BFS was efficient, that it's polynomial runtime, then we are done. We have shown that the algorithm runs in time O of n cubed. Any questions on this? Everyone okay? All right, so sorry I have to move things up. I'll kind of move back and forth a bit. Or so let's do our second analysis, where we want to argue that the number of times I get here is actually at most n squared. And the observation is the following. So now let's try to be, so the idea is what we came up as an upper bound of n cubed is definitely a correct upper bound. It's just that we are overcounting things by a lot. Okay. So what we want to do is slowly kind of nail down where we're overcounting and get better and better estimates. So here's one place to see where we are overcounting. So let's say let's say we're at layer, we have already created layer I and we're trying to create layer I plus 1. Okay, no, sorry. I'll change. Okay. So let's consider number of times this while and first for loop runs. Okay. So let's concentrate how many times can we get to here, right, which is T12. Right? So, okay, let me write down first thing and then, so I claim T123 is at most T12 times n. And just to be sure, why is that? T12 is the number of times I get here. And after I get here, this loop can run for at most n more time. Right. So the number of times the innermost loop runs, or sorry, the number of times the control goes to the start of the innermost loop is by definition T12. And the inner loop by itself can run for at most n times. Okay. So is this inequality okay? Are there any questions? Okay. So we now have that the number of times you get to this innermost guy is the number of times you get to this start of this loop, and this loop runs finite times, so this is at most this. But now I claim that T12 itself is at most n, and why is that? Well, let's try to, instead of thinking of the while loop and for loop as being independent, note that they are dependent, right? So what is the while loop doing? It's saying go through each possible layer, and then the for loop is saying is within each layer go through all possible vertices. So if you look at the combined effect, what it's saying is the while and the for loop is going through all possible vertices among all layers. But since each vertex is at most one layer, the total number of vertices among all layers cannot be more than n. So that's why T12 is at most n. So this follows from the observation that each vertex is in at most one loop, and that T12 is exactly equal to total number of vertices in all layers. Okay. So now when I have the T12 is at most n, n times n is n squared, and so that implies overall we have O of n plus O of n squared, which is O of n squared. All right, so we got some improvement, but we should be greedy, so we'll try to do even better. And this is going to be our final, so we're going to argue T123 is at most order m, which you can't see. So let's see. So sorry, hopefully you have this written down so you can refer to it. So we want to do an argument directly. So let me kind of walk through this on the pseudocode, and then we'll write it down. So the observation, so now I want you to think a bit harder about this statement. And so we said previously that the number of iterations of this innermost loop is n or n minus 1, but you can do better in terms of degree. So if I tell you to give me a bound in terms of degree, how many times would this guy run? Mark.
Every edge has to be u.
Yeah, which is the same as the degree of u, right? So in fact, if you look at this guy, this is exactly equal to nu. We run for exactly that many steps, which we can always assume is at most n. So this is kind of the one step that we'd ignored in our head when we said the number of times this runs is at most n. All right, so what's happening over here? So now if you want to do T123, is first you go through each possible layer. And so if you look at the definition, we said T1 is the number of times this while loop is run, which means that's the number of layers. So for each layer, you're looking at all possible vertices in Li, right? So again, here I'm just writing down what it would be. So there, for each iteration I, you're looking at each vertex u in Li, and once you get here, the number of times you run this is nu. Okay. So I claim that the number of times you run, basically go to the innermost part of the thing, is sum over all layers. Then you have a sum over all vertices in a layer. And then for each vertex, you have its degree. So I'll let you stare at it for half a minute. Let me know if you have any questions. Does this make sense? After this is just a matter of manipulating symbols and applying things that we already know. Mark.
Can it check every edge twice?
So Mark's question is, can it check every edge twice? The answer is yes, and that will come out in the next line. Okay, maybe let me just complete this. So we are first going to use the fact that every vertex is present in at most one layer, right? So this is at most sum over all vertices of n of u, and here we use each vertex in at most one layer. And now this we know is exactly 2m, because that's the identity that we proved. And so Mark, this is where it comes out. You can access each edge twice, but no more than 2 times. So in particular, the innermost part of your loop will run at most 2 times the number of edges that you have. And so of course, this is order m. So that implies overall you have order n plus order m, which is order m plus n. And this is our final thing. And as a quick note, remember that the input size, because this is an adjacency list representation, is theta m plus n, right? This is essentially m plus n. So what this means is these two things imply BFS is a linear time algorithm. Because the input size is theta of m plus n, and I can run the whole thing in order m plus n. Okay, so talk to your friends for half a minute, let me know if you have any questions. If not, we're going to move into kind of some quick variations of BFS and then do a quick analysis for why DFS also runs in exactly the same order m plus n time. Are there any questions? Alex.
What does M represent?
M is the number of edges in a graph, always, unless it says otherwise. Any other questions? Lloyd.
T1, 2, and 3 are just points of sort of loops.
So T1, 2, 3 is the number of times you get to this statement. So the number of times this whole block of code is run.
Just that.
Just this whole thing. Just the innermost part.
So why is it 1, 2, and 3 then?
It's 1 because I'm saying this is the first loop, this is the second loop, this is the third loop. Any other questions? So all good with BFS running in order m plus n? All right. So this is exactly what we just went through. I'm not going to go over it again. But basically, as a reminder, this CC is an array, and then you have a linked list for each layer that you're building. And basically, what I'm going to do is redo the entire argument that I just did in 5 seconds. Oh, by the way, as I mentioned in the book, they also consider a version which also creates the BFS tree explicitly, which we don't. So, or maybe I'm not going to do it again. I forget what I'm doing here. But so the important point to note is if you look at the various layers that you're considering in your algorithm, you first exhaust everything that's in one layer and then go to the next layer. So if you look, even though you're creating different linked lists for different layers, you always process one layer entirely before moving on to the next one. Right? So this basically allows you to say, well, I don't really need different linked lists for different layers. I can just have them in one big queue. Just make sure they're in the right order. Everything in layer 0 comes first, then layer 1, then layer 2, layer 3, layer 4, and so forth. So the basic idea is you just combine all layers into one. So I think I've gone through this bit quickly last time, so I'll go over again a bit quickly. So the way you do it is you first put your start vertex inside the queue, and the way the algorithm runs is you always pull the guy in front of the queue. So delete the guy in front of the queue, and the moment you do that, you put all of its children that have not been visited yet back into the queue. So in this case, that would be 2, 3. You look at the front of the queue, which is 2. Now the children of 1 are 1, 3, 4, 5, but 1 and 3 have already been visited. So I'll just put in 4, 5 at the back, right? I get 3 out, I'll add in 7, 8. I'll get 4 out, all the neighbors of 4 are done, so I'm not doing anything. I take 5 out, and I'll put the its only neighbor that has not been visited, which is 6 at the end. And at this point, I've visited all nodes. But the way you do, I mean, for the run of the algorithm, you just keep on deleting stuff from the queue. So you just delete 7, 8, and 6, and your queue is empty. At this point, you're done. Okay, so this is kind of the queue-based representation of BFS. How many of you have seen BFS based on this queue data structure before? All right, so this should then hopefully kind of reinforce that. All right, so here is how you would implement it as a queue. Oh, Stephen.
Yeah, is there a reason we're implementing the queue as a linked list
Instead of a what?
like as an array?
So the question was, is there a reason why I implement queue as a linked list as an array? Yes, because if you have to delete stuff from the front of the queue, and if it's an array, then you have to move everything up, right? And so that's order n time. And what you want to do is every insert and delete should be constant time in front and back of the queue. Sure. All right, so the first part still remains the same. You still have this array that tells whether the vertex has been visited or not. You initialize it just as before. The queue gets initialized with the start vertex s. And now you run this whole thing while the queue is not empty. So you run this whole loop while it's not empty. In every iteration of the loop, we delete the front guy, and then for if that vertex is u, you look at all neighbors of v and do the same thing. If the neighbor w has not been visited yet, mark it as visited and add w to the back of the queue. Okay, so this back is the important part. Okay. And so if you do the runtime analysis, initialization as before is O of n, this is O of 1. This innermost set of instruction as before is O of 1. Since you're running the innermost, the red part, the number of neighbors of u, that's n of u. So in particular, this entire block now is order n of u. Now it's much easier to see the previous step that I had done, right? Because it's saying I'm going to put in each node at most once into my queue, and I'm going to delete it at most once. So the maximum number of times this loop can run is n, because you can put in at most n vertices in your queue. So this whole loop is repeated at most once for each vertex. Deleting the front guy is O of 1. So Stephen, this is why we needed it as linked lists and not arrays. So in particular, this whole thing runs in times O of nu, summed over all vertices u. And so this is just pushing the sum inside. And here we're using the fact that the sum of degrees is exactly equal to 2n. Okay. So this is the analysis. This is a bit easier, I think, to see than the previous step. The reason I went through the longer version of the previous step is because that kind of thinking is going to be useful in other algorithms also. Okay. So, but for this BFS, this would be easy. Any questions? So those of you who had seen the Q version of BFS, did you see this runtime analysis before, any of you? All right, okay. All right, so we're going to quickly, and I have, I think, 2-3 minutes, that's going to be enough. We're going to argue that DFS also runs in order m plus n time. And so if you remember, the way we stated DFS was a recursive thing, right? What that really means is if you look at the call stack, you're using the call stack implicitly to run your algorithm. And the way to make that explicit is from a perspective of like writing code or whatever, or pseudocode, is you look at the BFS pseudocode and just replace the queue by a stack and you're done. That's the only difference between BFS and DFS. Okay. So here's a DFS run using an explicit stack instead of the implicit call stack. So again, we start off with 1 and we put that guy in there. Then we look at all of its neighbors, which is 2 and 3, and now we put it on top because this is a stack. And now we'll go to the top of the stack, which in this case is 2. And the neighbors are 3, 4, 5, and 1. Ideally, I shouldn't be putting 1 in back again. Oh, I'm not. It's good. So I put 4, 5, and 3. Top of the stack is 4. So I look at 4. The neighbors of 4 that have not been visited yet is 5. You might notice that I have 5 come in twice here, right? So there's a 5 here and a 5 here, but that's okay. Asymptotically, it doesn't make a difference. So you go to 5. The neighbors that have not been visited here yet are 3 and 6. So you go to 6. All the neighbors of 6 have been visited. So you go back to 3. The neighbors of 3 that have not yet been visited are 7 and 8. So you put 8 and 7. And then you go back 8. The neighbor that's not visited is 7, you put 7 on top, you mark 7 as visited. So now note that there are vertices that are repeated. So for example, 3 is here and 3 is here, but both of them are now marked as visited. Because I'll again have a separate CC array to keep track of that. And now what you do is just throw away 7, 8. So you just keep on popping the array till you're empty and you're done. So this is how you'd use a stack to do this. So if you look at the pseudocode for DFS, it's very similar to BFS. The only difference is now instead of a queue, I'm using a stack. And instead of taking from the front of a queue, I'm popping from the queue. Instead of adding to the back of the queue, I'm pushing it back to the top of the queue. So this is the only difference. Right? And the runtime analysis is exactly the same as before. Stephen.
Just curious about the level of that. Okay, stack. Would it still be order of n?
Sorry?
So the stack that you would have just had would have had more than n.
So the Stephen's question is how big can that stack get? It can get as big as O of m in the worst case. But that's still okay because the total runtime is order m plus. All right, so we are getting close to finishing chapter 3. So everything up to 3.5 is reading assignments. And I have solutions for homework 3 for you guys to pick up.